Okay, can you see the screen?
Yes, sir.
So today's topic is active load. Load is something that we connect to the output, right, of any circuit. So and here we have the amplifier, the common emitter amplifier, and there's actually no load connected. But when we do not have any load connected, then just RC what we have here, and that RC will work as the load resistance. And if you connect your load here at the output RL, that will come in parallel with RC, and that will work as we can consider that one single resistance. So that's why we are not considering any other additional resistance as a load resistance, just RC one single resistance. Because anyway, these two will be in parallel and they will work as one single resistance. So just RC here, and that's connected to the supply, and we take in the output from here. So this is RC is we know is a passive component. So that's why we can also call it a passive load. So this is a common emitter amplifier with a passive load. Now, first we will see what are the limitations of the passive load before we go to the active load, why we need active load or why active load is introduced. Right? So in this case, the gain of the amplifier, what we can write the voltage gain is V naught by Vi, and that is given as common emitter amplifier gain is minus Gm, and then we have small r naught times Rc. So that is the gain expression for common emitter amplifier. R naught is the resistance, right? That is connected between we have this at the output between collector and emitter of the transistor. So just we have R naught, right? So that R naught comes in parallel with RC. Right? So that's how the gain expression will be. Now, usually in most cases, what we get that RC is much smaller, or R naught is much larger than this. We can approximate to minus GMRC, right? Because in most cases, this R naught is much larger than RC. Right? So this is an approximation. Now, to get further insight into this expression of the gain, we replace GM by IC by VT. GM is IC, and we have RC, and IC by VT. So that's the expression for GM IC by VT, and then we get this expression. Now, if you look at the circuit, what is IC, RC? ICRC is this voltage drop, right? This voltage drop, and IC is the current, right, that is flowing here. So ICRC basically is this voltage drop. So interesting thing here to note that the gain of the amplifier is nothing but the voltage drop across this RC and divided by the VT, the thermal voltage. VT is constant. So for higher gain, what we need higher voltage drop across the ICRC. So that is what is the measure of the gain. Now take a typical numerical example. Let's say that our collector current IC is 1 milliampere and our collector resistance RC is 2.5 kilo ohms. So these are typical values for current and voltages, current and resistances in the electronic circuits. So with IC 1 milliampere, the VT will be uh, not VT. VT is usually 25 millivolt, or we can take as 0.025 volt. And GM, right? Okay, GM, we don't need GM. Just to straight away write the gain, voltage gain. Voltage gain is ICRC divided by VT, right? And IC here 1 milliampere, and that times 2.5 K is RC, and that divided by 0.025 volt. Right? So if you do the math here, this is here you get 2.5 volt and 0.25. So you get a gain of 100, about 100 volt per volt. And how much is ICRC? This is basically, if we take do the multiplication, that's 2.5 volt. Right? Now, why I am writing like this, 2.5 volt? Because from this we can understand the requirement, right, on the different the current voltages for the amplifier and power. First of all, the DC power supply here, right, the VCC. What should be the value of VCC, right? How low or how high it has to be, right? Okay, we don't need very high the power supply. The higher is the voltage level here, the higher will be the power loss. Higher the higher will be the amount of power that power supply has to supply, because the power that goes in, right, the input power to this amplifier is VCC times IC, right? That is the actually power that is being supplied to this amplifier by the power supply. And the higher you take this voltage, the more power the amplifier will consume. So one of the design aspect of the amplifier is to keep VCC as low as possible, the minimum that is needed, and right, and that is needed to for the amplifier to work properly for the whole range of the signal. So that minimum value should be used for this VCC. So what can be the minimum voltage in this case? Let's say for this amplifier, if you want a gain of 100, so what we see that the ICRC should be 2.5 volt for to achieve a gain of 100. So now 2.5 ICRC, the drop you have here. So then you need to have a similar amount of voltage drop across this VC, the collector emitter, this is not working. This is a problem. Okay, sometimes there's some malfunction and causes some problem. Anyway, so okay, now here what we have that no, it was for the other one. Okay, ICRC we have 2.5. So here VCE, right? So we need a similar amount of voltage drop across VCE, because so that your signal can swing in both directions. You have 2.5. If your signal swings in the positive half, then you need another 2.5, right? Voltage in the negative half cycle of the signal, right? So total the voltage that will be needed here is 5 volt, right? So this 2.5 will allow this signal to swing in the positive half for a maximum of 2.5 volt, and the voltage here VCE that will allow this signal to swing in the negative half cycle for the same amount of voltage 2.5. So 2.5 and 2.5 total will be 5. So at least VCC should be 5 volt in this case, right? So what we understand the requirement here to if you want to achieve a gain of 100, so at least the power supply that we need should be 5 volt. Right? Is that clear, guys?
Yes, sir. Sir, can we have different source voltages for any cascade configuration?
It's better to have the same voltage level for
Okay.
the power supplies, because if you have different voltages, then you need, let's say you're using two different voltage levels, right? So then probably you'll need two batteries, right, to power
Yes.
your amplifier. That is not very practical, right? So you're using one extra battery, so that will size increases, cost increases, so it becomes very inconvenient. Right? Usually you power up your device with one single battery.
Okay.
Right? So here the minimum you should use the voltage for the power supply is 5 volt. Okay. Now, what are the issues here? Now, see, if you want to use a gain, 100 gain is nothing for integrated circuit. So we want a gain of 1,000, right? We want a gain of 1,000. Op amps have gain in the range of 10 to 5, 10 to 6, right? So we're not going to that, right? We're just limiting ourselves to 1,000 volt. So if we need a gain of 1,000 volt, since if you see this expression, the gain expression here is ICRC divided by VT. VT is constant, 0.025. So to achieve a gain of 1,000, ICRC, or should be ICRC, should be 1,000 times VT. Gain is 1,000, and 1,000 times VT should be your gain. So VT is 0.025 times 1,000 should be 25 volt. Is that correct?
Yes, sir.
Now see the requirement here the for the power supply. Now for 1,000 gain you need 25 volt here, another 25 volt here. So the requirement on the power supply becomes 50 volt. Right? So is that a practical solution?
No, sir. The
So most of
25
the
arm.
right electronic devices, they are right different gadgets, they are powered up with a 5 volt battery, right? Even your cell phone. So that is not a practical solution at all, right, for electronic device that will need such a big power supply. So just for a gain of 1,000. And other issues, how do you increase this gain? I mean, get the high voltage IC/RC 25 volt. So either you increase the IC or you increase RC. Right? So neither is convenient or practical for integrated circuit. When you increase the IC, the I square R loss increases, because it increases with the square of the current. Before the loss, power loss was I square R, right? ICRC in this case. I was 1 milliampere. So that is just 1 square, and RC was 2.5, right? So that gives you 2.5, that will be milliwatt. And now if you want to increase the gain 1000 to 100, from 100 to 1000, that means you have to increase I. Let's say you're increasing I 10 times. So instead of 1 milliampere, you use IC of 10 milliampere. So then your loss will be 10 square times 2.5. So that will be 100 times 250 milliwatt. Right? So your power loss goes up from 2.5 to 250, 100 times. It increases 100 times. So you see that tremendous heat it will generate, right, in your IC chip, and ultimately it will destroy, damage your chip, right? So there's no way you can consider increasing the current to such a high level to increase your gain. So probably you will go for the resistance to increase, right? If you increase the resistance 10 times, so then you have to use, before it was 2.5, 2.5K. Now you can use a resistance to 10 times greater, 25K. So that will increase the gain by 10 times. And what are the downside of this one? Increasing the resistance will uh, take more space in the IC chip. So for 2.55K, whatever space it would take, for 25K, it would take 10 times more of that space, right? The space will be 10 times of that. So you see the chip area will increase, right? And IC chip, the aim is to keep the chip area small, but if you want to increase the gain, you need to increase the resistance and your chip size gets bigger. Right? Is that clear, guys?
Yes, sir.
So these are the different issues that we have with the passive load, that if you increase the current, right, the power loss, right, power loss will increase. And if you increase the R, right, your chip area will increase. Right? And in both cases, the power supply, right, whether you increase I or increase R, the requirement on the power supply also go up. Right? So these are the different limitations that we have, right, with passive load when you want to have a higher gain. Right? So that's why passive load, we cannot increase the gain beyond a certain limit, right? Maybe a couple of hundreds. Right? But if you want to achieve very high gain, so that is not possible with the passive load. So then the solution we get using the active load. That is So this circuit here, this explains the basic concept behind the active load. So here, instead of the resistance, we have at the collector of Q1. Q1 is our amplifier, and Q2 is our load. So instead of the resistance RC, we have a transistor connected. Transistor is an active device. So that is called the active load. So Q1 is our common emitter amplifier, and Q2, this is our active load. So Q2 is working as the active load. Now, how it is working as the load? Because now, if you look into the collector here, right? So you will see an output resistance, small r naught 2, right? So that will be connected between the collector and the emitter of Q2, and that is R02, right? So this R02 now will be like the load resistance, right, for Q1, right? Instead of RC, now we have R02, and that will work as the load resistance. And that is the resistance of this transistor Q2, and so the Q2 now we call the active load. Is that clear, guys?
Yes,
Any
sir.
question? Now, what will be the gain of this one, right? Now, here, like before, also we'll have the resistance, the R01, right? So now the gain of this amplifier, the voltage gain, which is V0 by Vi. Now, this one is minus Gm. The total resistance here is the parallel combination of R01 and R02. Okay. So we had R01 also in the previous circuit. If you go back, and that is way down, right? Let's okay. So in this circuit, what we see that we have this RC, and the gain was minus Gm R0 RC. So now this R0 is our R01, and instead of RC, we have R02, right? So that's the same expression. So that's the gain expression. Now we replace this Gm by IC by Vt, so we can write this IC by Vt. Okay, before that we need to do something. Now, for simplification of our calculation, calculation, we assume that these two are same. R01 is same as R02, and we can write as R0. Right? So the parallel combination of R01 and R02 you can write as half of R naught. Okay? And using that in this expression for gain, so again we can express it as minus half Gm R naught. Now Gm is IC by Vt. So we have IC by Vt. And what is R naught?
So PA by IC.
Right, R naught is Va by IC. So what we see that IC and IC will cancel out and we'll be left with minus half Va by Vt. Now, interesting thing here, so that is our gain expression. Interesting thing here that the gain is independent of the current IC. Right? Gain does not depend on the bias current IC. Right? So in the previous, for the passive load, so the gain was heavily dependent on IC. For higher gain, you need to have higher value for IC, and that would increase the the voltage drop and the power consumption, the requirement of the power supply, all these issues. But here you can have a very small IC, but still can have high gain, right? So, and keeping the power loss low in the amplifier circuit. So that is one big advantage of using the active load, right? So what's the gain in this case? VA is, we know, is usually high. Let's say, let's assume that this is 100 volt. And VT, as before, we assume 25 millivolt or 0.025 volt. Right? So with these values assumed, so what will be the gain for this? So we have minus half, VA is 100 volt and VT is 0.025 volt. And if we do the calculation here, it will come about 2000 volt per volt. So you get a tremendous improvement over the amplifier with passive load, right? Therefore, even for 1000 gain of 1000, you needed a power supply of very high voltage. Now, just with 5 volt or 3 volt even, right? You can have a gain of 2000, right? So that is a tremendous improvement. Is that clear, guys? Any question?
No, sir, no question.
Sir, why PNP transistor?
You cannot use an NPN in this case because the current has to flow in this direction, right? All the way, right? And here you cannot connect if you use the NPN, then the emitter will be here, right? For the current to flow in this direction. And if you connect emitter here, emitter has a very low output resistance, RE, right? Emitter has a very low output resistance. And so that load resistance will be very low and gain will be, very low. Did you get the idea?
Yes, sir.
It will not work with the NPN. So this is an example where you need PNP, right? It will not work with NPN. Because at the load you need high output resistance, right? And on the collector, from the collector side, you get the high output resistance. So you need to connect the collector of the transistor with the collector here of this Q1, right? Then you get the high output resistance R02. You can't connect the NPN for it because also current has to flow in this direction. And for the current to flow in this direction, then you will connect the emitter of the NPN transistor here. Right? But at the emitter, the output resistance, you have R02 also in that case, but that will be in parallel with RE, small RE. So R02 will be, it will not be effective. Right? So
Sir,
only R, yes.
in DC voltage level shifter, we showed the direction of the current in opposite direction. Like it was coming from VCC.
Yeah, this is it. Yeah.
So in this case, the current direction is opposite.
What do you mean opposite?
I mean, the current is going from
The IC flows in this direction, no? This is the positive direction of IC. So it has
yes,
to flow in this direction, right? If you use NPN and collector here, and then your emitter will be here, right? And arrow is pointing that way, right?
yes, sir.
So here the current has to flow up, not down, right? And this is not work because here the current has to flow down, it has to flow up. So both will actually remain off.
Okay, yes, sir. Got it, sir.
Okay. Okay, so that is the basic concept of the active load, how active load can help improve the gain, achieve a very high gain without, the heavy requirement on the power supply or the bias current, right? And, the power loss in the circuit, right? Now, what is the actual circuit? How it will look like? Right? Now, how do you? This is just the load, but you need to supply this transistor with a predictable this current, bias current IC. Right now, there's no mechanism of that. Right, so you need to have a mechanism to supply this transistor with a suitable bias current IC. Now, how do we achieve that? Now, what is this Q2 and Q3? What do they make?
So current mirror.
Right. These two together make the current mirror circuit, right? So Q2 and Q3 is the current mirror circuit. Among this Q3, that establishes this current IR, right? And since this is a current mirror circuit that has the same, here the emitter to base voltage, right? The bases are tied together. So they will have the same collector current. So this IR will be reproduced here in Q2, right? So I will be equal to IR, right? So that's how we can supply the required bias current to the transistor Q1. Now, what will be IR in this case?
So VEB by R.
VEB by R, are you sure? VEB is the voltage here, no?
Okay.
So if you know the voltage at this end, right? The voltage is a VC, right? The collector voltage, then you can write IR will be VC by R, right? And what will be VC?
C minus VEB.
Will be VCC minus VEB, that divided by R. So that will be the collector current, sorry, the current here at Q3. So that's called the reference current. So by adjusting the resistance R, you can fix this current, reference current, and that same current will be reproduced here. So that is how the current mirror will, supply the necessary bias current to the transistor, this Q1, and at the same time, it will also work as the active load, right? The output resistance here for the Q2, the R02, that will be working like the active load. So the current mirror basically will serve the two purposes for the amplifier, in this case, supply the bias current and work as the active load. Is that clear?
Yes, sir.
Now, in our discussion on the current mirror circuit, we have discussed the different ways to improve the performance of the current mirror circuit. So if you want to apply those different techniques here, how we can do that, let's see that. We discussed about introducing the resistance in the emitter. To reduce the error due to the finite output resistance. So if you want to do that, so you can add resistances in the emitter. RE and RD. So in that case, the output resistance that you will see here, let's say this is we called R02, right? And here this is R01. Then effective your load resistance will be, this will change, right? This will be R01 in parallel with R02. Now R01 is same as before, small R naught, but R02 will be not, now will be different, right? So that will be R naught 2 and that times, right, 1 plus GM, in this case current GM2, and then RE, that will be in parallel with R0, sorry, R pi 2. So that will be the total resistance, output resistance R02. And if that is much larger, right, if that is much larger than R01, because we just R0 not, and that being multiplied, if we consider that that is much larger, then your total gain can be approximated to, instead of R naught, we can write here R02, right? There's one thing we need to change here. Will not have this half, right? So that will be minus GM R02. Is that clear, guys?
Yes, sir.
So that gain will be larger, right? What we had before. Right? Before the gain was, okay, that will be greater than what we had before, which is minus half, which is half GM R0, right? So that because this is now getting multiplied by this additional factor, right? So with that modification, we get an even higher gain and improved performance for the current mirror. And that reduces the gain, reduces the error due to the output resistance. And you can also add the other modification to reduce the error due to the finite beta. And for that, this is right, no? So that is our beta helper circuit, right? To reduce the error due to finite beta. So that's our Q4. So in this case, the base current will be flowing in this direction, right? IB and IB. So we need this again PNP transistor so that current, right, total current flows in this direction. Any question, guys? No question. Okay, now.
No question, sir.
That's good. So let me ask one question. What will be current IR now?
Sir, IB is equal to will be I by beta plus 1.
Hmm?
2 IB by beta plus 1.
Let's say we don't know beta, right? And then again, you need to find IB. Then the question will be what will be IB, right?
Yes, sir.
The same as before, we just start with VC by R, right? The voltage at this point collector, the VC. So this voltage divided by the resistance, R is the current. Now, what is the question? What is VC now, right?
So now VCC minus VEB minus the voltage drop in Q4. What will be also another VEB?
VCC minus VEB minus
Sir, VEB.
VEB. So that's VCC. Is that correct?
I think so.
VCC minus VEB. VEB is the voltage drop here. Uh, so there is the voltage drop here, VEB, right? And then you have another VEB drop here. Right? So there are two VEB. And what would the drop here?
Sorry, in RE,
Hmm?
IERE.
So you didn't consider that, no?
Oh, no, sir. Oh, yes, sir. I should consider that. Then minus IERE also.
So basically, you will have you have VCC. Okay, let me change. VCC minus uh, IERE minus 2 VEB, right?
Yes, sir.
So the question is, what is IE, right?
Yes, sir.
That's not a difficult question because you see, this is the collector current here, and this is the emitter current, and the IR is, we say, the IC, which is alpha IE, and that will be alpha IE, right? And that we can alpha assuming 1 to be IE, right? So you can take IE for, right, same IR, right? Assuming same current is flowing, alpha assuming 1. So if you do that, then IR we can express as the actually the VCC minus the total voltage drop here, which is VCC minus 2 VEB, the voltage drop in the two PN junctions, and that divided by the total resistance here, which is R plus RE. Is that clear?
Sir, where that R came from? Oh, okay, okay, got it. Got it.
Yeah, you can use this equation here, right, and solve for IR, or you can directly write this one, right, by just looking at the circuit, right? The total voltage across these two resistors combined would be the supply voltage minus the voltage drop in these two PN junctions. So that will be total voltage drop. The total voltage drop divided by the total resistance. So that will be your current IR. Is that clear?
Yes, sir.
Okay, now we see an improvement of this current mirror circuit. Sorry, improvement here, active load using the current mirror, right? So what is this circuit? Hmm? What circuit we have used here as the load?
Sir, current mirror circuit.
It's the cascode current mirror.
Okay, cascode current mirror.
So we have used cascode current mirror as the active load. Now here the resistance, let's call it R02, and the resistance here is R01. Now R01 remains same as before R0, R01, right? And R02, what will be R02?
Sir, R not 2 plus R not 4.
R02 plus R04. Okay. The cascode configuration has a current gain of R0 times 1 plus beta.
1 plus beta.
Right. So that is the output resistance cascode current mirror that we have discussed before, So that is, you see what is the resistance here, R04, right? That is connected as a, right, at the emitter of this. And then R02 basically will have this form R02 times 1 plus GM, right? GM2 times R04 in parallel with R by 2, right? And this you approximate to R02 1 plus GM2 R by 2, right? So GM R pi is beta, right? So you can write if you just remove subscript 1 plus beta. Right? So that's the output resistance for the cascode configuration. Any cascode configuration has a tremendous output resistance R naught times 1 plus beta. So you take the parallel combination, the R01 and R02. You take this parallel combination. Parallel combination will be always R02 because that is much larger, much larger than R0. Right? And that we can just write R01 plus beta. Right? Assuming we just is that clear? So in this case, the gain expression, so voltage gain is minus half GM, and you have R01 in parallel with R02. Now together this is, and you take parallel combination. Oh, I made a mistake here. What will be the parallel combination here?
Sir,
This one.
R not,
Parallel combination is
R not 1.
R not 1. Yeah, that's a mistake I made here. It's R parallel combination R not 1. And R not 1 we can just write as R not. So that will be minus half GM is R not. So we get, is that correct? What did we get half? We don't have it. So that's the voltage gain minus GM. There is no half. Sorry. So what we get here is minus IC by VT, GM and R naught is VA by IC, and so we get minus VA by VT. And assuming VA to be 100 and VT 0.025 millivolt, sorry, 0.025 volt, you get minus 4,000. So in this case, you see that the Q1, the output resistance of Q1 is much lower than the output resistance of the cascode current mirror. So the gain of the amplifier is mostly determined by the output resistance of this Q1. Now, if you can increase the output resistance, it is possible to achieve even higher gain. It is possible to achieve even higher gain. Now, how do we do that?
Sir, what will we do with this much high gain?
Yeah, you sell some of this if you don't need that. How much gain you have in the op amp?
Sir, in
Hmm?
pence.
What?
Sir, pretty high gain.
Yeah, it's 100,000 or million, right?
Yes, sir.
And we are only in the range of 1,000 now. See,
Okay.
this is 2, 6. So here you have the bias voltage. Now, what is this one? Q1, Q6 together, what do they make? This is a cascode amplifier, right?
Yes, sir.
Right. Cascode amplifier, and you have the cascode current mirror as the active load. Right?
Now, cascode amplifier with cascode current mirror.
Yeah, yeah. So now you have both R01 and R02 will have very high values. Now R01 will be also small r01 times 1 plus beta. This is also a cascode configuration, and that will be the output resistance. And so the parallel combination so the parallel combination here is R01 plus 1 plus beta, that's in parallel with R02 times 1 plus beta. Now, assuming R01 and R02 same as R0, so we can express this like this parallel R0 times 1 plus beta, and that gives you half R01 plus beta.
Open the door.
Yes, sir.
Give me a minute. I'm coming. Okay, so this is when you take parallel combination, that is half r naught 1 plus beta, and so we get minus half gm r naught 1 plus beta. Right, so you have minus half gm is ic by vt and va by ic times 1 plus beta. So we get minus this is va by vt, right? And 1 plus beta. So VA is here, let's say 100 volt, and VT is 0.025, and if beta is 100, then we get this. So we get minus half, and 100 divided by 0.25, we get 4,000 times 101. So overall gain will be about minus about 200,000, right? So a tremendous improvement in gain, right? Any question? Is that clear? Okay. So that will be our end of today's lecture.